Today we'll be practicing 3 different types of linear regression problems together to help you understand the concept of linear regression and prepare for assignments, exams, and real life. The first problem that we'll complete together will be a plain old linear regression problem. We'll show you how we would solve the linear regression problem by hand, which is useful for an exam. But realistically, for a job, you'll never complete linear regression by hand. You'll always use Excel or some programming language such as Python or MATLAB. So what we're going to do for question 1 is that although we're solving by hand, we'll also provide you with a video link where we solve for the linear regression equation in Python. The second and third problem are really interesting, and I would really emphasize that you look at them because these are problems where you have to use linear regression to fit to non-linear expressions. So what you're going to have to do is linearize first. And we consider questions 2 and 3 to be more curveball-like questions that you could see in assignments or exams. So we encourage you to check it out. We've divided this video into sections, so you can skip between problems as needed. But before we get started, please hit like and subscribe to our channel. So let's start by solving question number 1 together. Part 1 of question number 1 says, use linear regression to fit to the provided data. So here you'll see that we have data relating temperature to the revenue of ice cream sold. So as you can see, as the temperature increases, more ice cream is being sold. Here you see the 2 equations that we discussed in our theoretical video on linear regression. So now we'll just apply these 2 equations to calculate our slope and to calculate our y-intercept. And like I said, I'll show you how we can do this quickly for an exam. That being said, in reality, for practical purposes, it's most likely that you'll be completing linear regression fitting using a program such as Excel or a programming language such as Python or MATLAB. So enough jibber jabber, let's get started. The first thing we're going to calculate is the slope. So we're going to make sure that we calculate each component to find the slope. And what I recommend you do if you have to calculate this by hand in an exam is that you make a table where you write down each of the entities you need to compute. So we'll just start by going through these different components one by one. So first of all, n represents our number of data points. So we just calculate 1, 2, 3, 4, 5, 6. So we have 6 data points. I'll write down here n equals 6. Then we'll move on to summing our xi, yi data points. So what I'm going to do is I'm going to multiply each of these xi, yi pairs and write the result in these different rows. And then in the end, I'm going to sum it up and write down my answer. So let's just do the first one together. 15 times 35 equals 525. 19 times 50 equals 950. And I'll just write down the rest of the entities. So when we add up all the values in our column here to get our term, we get an answer of 12,393. Moving on to the next term, the sum of xi, all we have to do is add up these values here, and we'll get an answer that our sum equals 149. Adding up all our y values here in this column, when doing this, we get an answer of 460. Here we have to square each of the xi values and then add them up. So again, I've dedicated a column where I first square each of these x values and then we'll add it up at the end. So 15 squared is going to equal 225. 19 squared equals 361. And I'll write down the rest of the values. And adding up these values, we get an answer of 3,979. So with this, we've calculated all the entities we need for our slope. So substituting the values into our slope equation, we get n equals 6 times the sum of xi, yi, which equals 12,393, minus the sum of xi, which is 149, times the sum of yi, which is 460, divided by our number of data points times xi squared, which will equal 3,979 minus, and we forgot one last term. We need to take the sum of our xi, which we see is 149, and square it. So I'll just write down 149 squared equals 22,201. And so when we type this into our calculator, or if you're doing this in Excel, you can just follow this format here and then choose the cells to write down this equation. We get an answer that our slope equals 3.48. So within a couple minutes, we were able to quickly calculate this A1 value, so our slope. Now we look at calculating our y-intercept. So for our y-intercept, we need to know the mean of our y data points and the mean for our x data points. So we'll look at the mean of our y data. It's just simply the sum of our y data divided by our number of data points, which equals 460 divided by 6, which will give us an answer of 76.7. Doing the same for our x data over here. We know the sum equals 149 divided by 6, which gives us an answer of 24.8. And so substituting this all into our y-intercept equation, we get that our A naught equals our mean of the y value, so 76.7, minus our slope that we calculated, the A1, 3.48, times our x value, 24.8. When we calculate this, we get that our y-intercept equals negative 9.69. So as a last step, I'm just going to write down the equation of our linear regression line to best describe the data. We get y equals 3.48x minus 9.69. And with this, we've solved for question number 1. So what you'll notice is that we haven't used this yi squared column yet, but the reason why we have it here is to compute our coefficient of determination, which you will recall is just a fancy word for our r squared value. So let's do this together as a next step. So what we've done now is we've written down the equation that we discussed together on the coefficient of determination. So if you don't know how we got this equation, we have a video that helps explain the coefficient of determination of the r squared. So all we're going to do now is substitute these different values, many of which we already computed for our linear regression line. The only missing values that you'll see at the moment is that we haven't accounted for these yi values. So this is, like I said, why we have this column here. So let's just go ahead and already compute our yi squared values. So again, I'm just taking these y values and squaring it. So 35 to the power of 2 equals 1,225. 50 to the power of 2 equals 2,500. And we'll do the same for the rest of the y values. So adding up all of these yi values squared, we get an answer of 39,106. The last item we'll need here is the sum of yi squared. So now I'll just take this value here, 460, and square it so that we have it right away. And we get an answer of 211,600. So now we'll just substitute everything into our equation for r. So we have 6 data points. The sum of our xi, yi equals here, these 12,393. We subtract our sum of xi, which is 149, sum of yi, which is 460, and we divide it by these square rooted values. So 6 times sum of xi squared, so we're referring to this value here, 3,979 minus summing the xi first and then squaring it, so 22,201, and then the same for our y values. And so then when we solve for our r value, we get an answer of 0.937. And the most important item to keep in mind is that at the moment this is just the value of r. For our coefficient of determination, or r squared, we need to square this value, so don't forget it for a test. R squared equals 0.937 squared, which equals 0.878. So with this, we've solved part 2 together. So we see that there's a reasonable fit between our data points and our linear regression line. The last part of the question simply asks us, how much revenue can we expect when the temperature is 24 degrees Celsius outside? So all we simply need to do here is take our linear regression line from part 1 and substitute in our x value our temperature of 24 degrees Celsius. So let's just do this together. Y equals 3.48 times 24 for 24 degrees Celsius minus 9.69. And when we calculate this, we get an answer of 73.83. Just put down dollars. So with this, we've answered the question for part 3. As a last note, having completed this linear regression problem together, all I wanted to show you once more was the plot of revenue versus temperature in case you're interested. So here you see our red experimental data points and our linear regression line. And what you can note here is that there's some offsets. So for instance, at 22 degrees Celsius, the line doesn't necessarily predict this experimental data point here, but this is the optimal fit. Another item I just wanted to point out once more as well is extrapolation. So one item that we have to be very careful with is that we've put together this linear regression line, but we've only fit this line to points between 15 and 35 degrees Celsius. So what were to happen if we wanted to calculate our revenue for 0 degrees Celsius? So here our x value would equal 0, so this term would disappear. So if our temperature is 0 degrees Celsius, we're earning a revenue of -$9. So as you can tell, this really doesn't make sense, and so you have to be extremely careful when using the linear regression line outside of the range to which it was fit. One last item to note for solving this question number 1 per hand is that we had to complete a lot of computation steps, so we had to type in a lot of values in our calculator, which can lead to errors. So in a separate video, what I'll show you is how we can easily compute our linear regression line as well as our R² value in Python. And I'll post the link in the upper right hand corner of this video right now. In question number 2, we're going to use least squares, or more specifically linear regression, to fit the provided data, so our temperature and rate data, to the Arrhenius equation, which we see here. So don't worry if you don't know what the Arrhenius equation is. The main thing to note is that we have this equation here, and it's certainly not linear. We have the exponential function, and we need to use linear regression to determine this coefficient a and ea. So we know our data k, and we know our data t, and we have a constant r. So how are we going to go about this? Well, as you may have learned in your numerical methods course, what you can do is that you can linearize this function. So we need to linearize to be able to use our linear regression equations. So let's look at linearizing this first. Since we have this exponential function here, what we need to do is we need to take the ln of each side. So we have ln k equals ln a times e to the negative ea over rt. And of course, if we multiply within a ln function, then we can add each of the elements. So we have ln k equals ln a plus the ln of our exponential function. So I'm really writing this out step by step to show you what I'm doing. And as a last step, we know that this here goes to 1 and we're left with this expression here. So ln k equals ln a plus, and I'll write this expression a little differently so that we're able to follow easily. I'm going to group my constants together, ea and r, and I'll make sure that we clearly define our x, 1 over t. So as you can see, we now have this linear function here. And what I'll do is I'm going to write it in the form y equals our intercept a0 plus our slope a1x. And so we'll see that our ln k will equal our y value. The ln of our coefficient a is going to equal our a0. This activation energy, or EA, divided by r will equal our slope, a1, and 1 over t equals x. So looking at this data, we have our temperature and we have our k value. So these are just referring to our x and y values. And so to be able to apply the equations we have for linear regression to this function here, what we need to do is we need to transform our y values to equal ln k and our x values to equal 1 over t. So here on this slide, you again see the expression that we had just written down. And what I've done is I've extended our data, our xy data, and we've transformed them to our new xy data points seen here. So how did we do this? This data point here, our 1 over t, simply equals 1 over 400. So we're just saying our new x data equals 1 over t. So likewise, this 2.22 e to the negative 3 equals 1 over 450. We've transformed our y data to our new y data by just taking the ln of each element. So here, this first value will equal the ln of 0.13, and so on. So like I said, this here is our new x data that we're going to use. This is our new y data. And knowing this, all we have to do is simply apply our linear regression equations that we used in the previous example, or you can also do it in Python using these values here as your x and y to calculate your y-intercept and your slope. So we won't write down these steps since we've done it in detail for the first example, and we think that using an approach such as Excel or Python or MATLAB or any other form of programming language makes more sense. I used Python, so what I'll do is I'll upload the Python script used to calculate the linear regression equation to our stem-tutorials.com website, and I'll post the link below. And so if we complete our linear regression calculation, we'll get the equation that our y equals 16.2 minus 7,286x. And so with this, all that's left to do is calculate our a and EA values. From this expression, we know that our y-intercept equals our ln a, which equals a value of 16.2. So let's write that down over here, that our a0 equals ln a, which equals 16.2. So if we were to rearrange for a, we simply have to take the exponential of 16.2, and then we have that our a value equals 1.09 times 10 to the 7. And with this, we've already simply solved for our coefficient value a. If we go on to do the same for our EA value, again, our coefficient equals this value here. So we'll just write it down that our a1 equals negative EA over r, which equals a value of negative 7,286. And so if we rearrange and know that r equals 3.145, then we get that our EA will equal 7,286 times 8.3145, and we get an answer that our EA value equals 60,579. And so with this, we've solved for both coefficients, and we've completed the problem. Finally, I would always recommend that you plot your experimental data and your linear regression expression at the end to check what does the quality of the fit look like. So here you see a plot of our K value, our reaction rate, versus our temperature, and you see the experimental data points as well as our linear regression expression, and so we see that we have a pretty good match. So with this, we've wrapped up the second problem, and we've shown you how we can transform these nonlinear equations into linear equations and then apply linear regression. In question number 3, we use linear regression to fit the tabulated data to the equation below. So here we see our equation. Clearly it's not linear. We're going to have to linearize first. And we see that we're given the data c and k. So here we have our c and k variable, and we need to determine the coefficient a and b. So the reason for including this problem in our practice set is to practice linearizing once more. And now we don't have an exponential, but rather what we need to do to linearize is take 1 over both sides of the equation. And then we'll get that our 1 over k equals b plus c squared over ac squared. And so if we split this into adding two fractions, we get that 1 over k equals b over a 1 over c squared. Again, I'm going to split it into two so that we have our constants grouped together and our x-like variable grouped together, plus 1 over a, and the c squares go to 1. And so if we again consider that our y equals our slope, a1x, plus our y-intercept, a0, then we see that our 1 over k equals y. The b over a corresponds to our slope constant a1. 1 over c squared is going to be our x for this linearized function, and 1 over a will equal a0. And so like before, we're going to take our x and y values, we'll transform them into our new x and new y values that we'll use for linear regression. So here on this slide, what I've done is I've just written down the expression that we discussed before, and now I've also calculated the 1 over c squared values and 1 over k values. So again, I'm just going to write it down like before. This first row value of 4 equals 1 over 0.5 squared. So this is going to be our x new data that we're using for our linear regression. And the 1 over k value is simply equal to 1 over 1. Or in this row here, it's going to equal 1 over 3.5. So with this, we'll have our new y data that we're going to use for linear regression. So again, it's up to you how you compute the linear regression line. You can do it by hand, or you can do it using a tool such as Excel or Python. Again, we'll upload our Python code that we use to our website, stem-tutorials.com. And when you complete the linear regression process, you'll see that your final equation equals y equals 0.224x plus 0.094. And with this, all we need to do again is back calculate our values for a and for b. So we'll do this together quickly. We know that our y-intercept equals 1 over a, which equals the value of 0.094. And so if we rearrange, our a will equal 1 over 0.094, which equals 10.6. And with this, we've calculated our a value. Looking at b, so looking at this term here, we know that our b over a equals 0.224, our slope. And so rearranging, we get that our b equals 0.224 times the 10.6 we just calculated for our a. So our b will equal 2.37. And with this, we've wrapped up the third question. This wraps up today's tutorial. We would kindly ask you to support us by hitting the like and subscribe button. If you have any further questions, please write them in the comments section below and check out our website, stem-tutorials.com. Have a lovely day.